Kind of difficult. These kind of problems are in algebra courses, but not to this extent, not with derivatives. But we always ask our students, even if they don't know what's really happening here, we just think of, and here's the question, according to the model, what happens to the yeast population in the long run? In the long run, what happens? In other words, when t approaches infinity, this is what we mean in the long run. But my algebra classes don't know the concept of what. What am I getting at? What am I really asking you to find? What happens in the long run? What am I really saying? Please find what? Find the
limits.
Excellent. When t approaches
Infinity.
Great job. That's what I can say to my students in algebra. So limit of f of t when t approaches infinity. So we have, I'm going to put the function now, limit as t approaches infinity, 140, 1 plus 6 e to negative 0.7 t. Okay, so let's find this limit. Okay, so when t approaches infinity, where does this go? When t approaches infinity.
Negative infinity.
Great job. Where does e to negative infinity go?
0.
Excellent. So then this piece is 0. How much is 0 times 6?
0.
How much is 140 over 1?
140.
What do we call y equals 140?
The y-intercept? No.
When t approaches infinity,
Horizontal velocity.
the function values get closer and closer to 140. If you want to convince yourselves, be careful. So in y equals, let's put in this function. Be careful how you put it in because you need parentheses around the denominator. And I will, no matter what, put parentheses around the power. That's me. Sorry about that. So 1 plus 6 e in parentheses negative 0.7 x. Close the parenthesis for the power and close the parenthesis for the denominator. Let me know if you have this. 140 over 1 plus 6 e to negative 0.7 x. Close the parenthesis for the power. Some calculators don't need parentheses for the power. If you know it's okay, skip them. But you need parentheses for the denominator. I will put the second function 140 because I want to see the horizontal asymptote. And now I have to work on the window. I don't care for negative 10. I can have time negative 10, right? So I'm going to put 0. X maximum, I don't know how fast it will converge. So I'm going to start with 50 with a scale of 10. See what happens. Y minimum, we're not going to talk about that because it cannot be, I cannot have a negative number of cells. Y maximum definitely has to pass 140. So I'm going to put 150. Oops. 150 with a scale of 25. And now I'm ready to hit graph. Here comes the horizontal asymptote. I didn't really need to go that far. So I'm going to come back and say, okay, maybe just 20 with a scale of 2. Better graph. And here comes the horizontal asymptote. These are logistic growth models. Any questions on this problem? Any questions? Okay, we're going to come back to this section for something very important with cost function that I would like to talk about, but I want to talk about, and I'll come back, promise, but I want to show 3.10, at least part of 3.10, which deals with, and then we'll come back to this section 3.7, linear approximations and differentials. So 3.10. And differentials. Okay. So let's take a look at the following situation. Yes, back to that function. This is x. This is p. Of course, this is f of x. And of course there is q, and of course q is very, very close to p, but allow me to zoom in, because if I put q here, you won't be able to explain anything. So we are zooming in, and this is q. And you're going to say, I know, it's x plus h. Well, we are changing the notation, but yes, it's the same thing. We're going to call this delta x or dx. So this is x plus delta x and x plus dx. In case you're asking why delta is this and not is this is the uppercase and this is lower. Both are delta. Uppercase delta, lowercase delta, from the epsilon delta definition. We use this in chapter 2, but this is uppercase delta. Okay, so obviously this is f of x plus dx or f of x plus delta x. Okay. Remember, they are very close to each other. We are going to call this dx, which is the same with delta x, minor error in x, like we did before. We just, at that time we called it h, lowercase h, instead of delta x and dx. However, they also have different names. They will be the same value-wise, but they have different names. Delta x is the error in x, and dx, although it's the same and it's the same value, it's called the differential of x. Dx, differential of x. Error in x. Now, what does this differential mean? A difference using derivatives. That's what it means. They put the difference and derivatives together somehow and they came up with this word differential. It's still a difference. This is still a difference. If you want tolerance, if you measure something, or a difference or an error in x. But this one is specifically determined using the derivative. It's not the exact. It will be the same in these situations, but because it's determined in the same way. But basically, this will involve derivatives. When we talk about this, we talk about derivatives. When we talk about delta x, we talk about the function itself. Still a difference, but the function. The same thing, but the derivative. Okay, fine. Let's go back to our graph. Let's suppose I draw the tangent at P. Here's the tangent at P, and I'm going to extend it all the way past Q, and I'm going to extend the vertical line through Q. Okay, now we have to do define two more things, and then I'll go back to the graph. Here's number one. Delta y, exact difference in the function values when dx or delta x happens. So there is an error in x. Any error in x will trigger an error in y. If q is p, there is no error. There is no error, no change in x, no change in y. But if there is a change in x, that will trigger a corresponding change in the y values. How big? This big. So what is delta y equal to? Delta y will be f of x plus delta x minus f of x. Is this piece? F of x plus delta x minus f of x. This is the exact error. Fine. Now let's go back and look at my graph again. I will extend horizontal line, and I will take out of here in a moment this triangle so I can talk about it more. But obviously this is this, which is delta y. So for a minor error in the x, in the reading of x, I have an error. I did not read the x correctly. I have an error. That will trigger this error in the function value. And this is the exact. Okay, now I'm going to take this triangle out because I don't want to put more stuff in there. This is Q here, but I'm going to call this A. I'm going to call this B. So I have the triangle PBA. PBA, which has this which we will find in a moment, and it has this piece which is delta x or dx. So I'm going to say this is dx. This is something I don't know yet. We will in a minute. And I am going to ask you to give me now the slope of the line PQ. The slope of the tangent line PQ. Number one, from this triangle, of course, which is a right triangle. And number two, from the graph. So, can anyone give us the slope of the tangent line at P? Can anyone give me anything that will represent the slope of the tangent line at P? Anything?
Is it dx over dy? Or delta x over delta y?
We're not there yet. You're way ahead of me, but thank you. Okay, so can anyone give me anything that I could write that represents the slope of this line? Anything from what we've studied so far in 2 chapters. We know how to write the slope of that tangent.
Did you say the limit of f of x as d of x approach or
Oh,
dx
we passed limits. We are in chapter 3, but you're right. But beyond that now, in chapter 3, we studied something else.
Is it f of x plus d of x minus f of x over x plus d of x?
With a limit, that's fine, but we already know something else. Agreed. But we learned in this chapter something way simpler than that. It's f prime of x, right? It's f prime of x. The slope of the tangent line at this point is f prime of x. So the slope is f prime of x. Correct? We agree? Whatever x is, the slope of the tangent line must be f prime of x. Once I have f prime, I plug in this value and I get the slope. Is that correct?
Yes.
Perfect. Now, awesome. I want you to give me, you do not know that. But I would like you to give me the slope, I should say, in this case, to give me the slope of this line as rise over 1. Rise over run. So you don't know what that is, but you know that the run is dx. Agreed?
Yes.
Good. What should I have here? What is the only thing that will fit in here? Look at what we have on paper and say, there is only one thing. And what would that be?
dy.
So this is dy. But what is dy? Of course, it's the differential of y. What does it mean? It's the difference in y using the derivative. So dy, differential in y, the difference in y, of course, which means using the derivative. So a long time ago, I said, remember f prime of x is the same with dy over dx, but I never told you till today, till now, that this has a meaning, which is this, and this also has a meaning, which is this. I only told you this can be replaced by that, but now they do have meanings. Dx is the difference in x using the derivative, and dy is the difference in y using the derivative. dy is this piece. I'm going to come back to the actual graph, and dx is this piece. Okay, what's all this theory? Nice, that's beautiful, but what does it mean? So this distance, which is this here, is the differential of y. This distance, which is this, is the actual difference in y values. The point we're making is, since q is very, very close to p, they are almost the same, not quite. So from here we conclude, remember I zoomed in, so what I'm really saying, the q is very close, so these two have to be close to each other. So what I'm really writing here is that delta y is approximately dy. The actual difference, which is f of x, and now I'm going to write it with dx, minus f of x, is approximately dy. But we haven't discovered what dy was yet. Can anyone solve this equation for dy for us? And that will be our dy.
Multiply both sides by dx.
That's it. Excellent. So dy equals f prime of x dx, and I'm going to write it here, f prime of x dx. So, before I come back to this super important relationship or result, I want to make a distinction between derivative of f of x and differential of f of x. They are two different things. The first one is f prime. The second one is dy equals f prime of x dx. So please understand the difference between these two.